I am Michio Kaku, and today a question stands before humanity that could redefine our place in the cosmos. Was it merely an interstellar object drifting through space, or was it something far more profound, an alien probe? In October 2017, astronomers operating the powerful survey telescope known as Pan-STARRS detected something unusual streaking across the sky. At first glance, it appeared to be just another asteroid. But within days, the data began to tell a very different story. The object was named ʻOumuamua, a Hawaiian term meaning a messenger from afar arriving first. And indeed, it was the first confirmed interstellar object ever observed passing through our solar system. But this was no ordinary space rock. Its trajectory was hyperbolic, not elliptical like the asteroids and comets bound to our sun. That meant it did not originate here. It came from another star system, traveling for millions, perhaps billions of years before briefly visiting ours. Already that fact alone was revolutionary. Then came the shape. Observations revealed extreme variations in brightness, changing by a factor of 10 as it rotated. This implied an object unlike anything commonly seen in our solar system. Some models suggested a cigar-shaped body, elongated and narrow. Others proposed a thin pancake-like disk. Either way, it was extraordinary. Nature can produce many wonders, but such geometry is rare. And in science, whenever anomalies appear, serious questions must be asked. Then came the most puzzling detail of all: acceleration. As ʻOumuamua moved away from the sun, it exhibited a slight but measurable non-gravitational acceleration. Comets can do this. When solar heat vaporizes ice, jets of gas push them forward like miniature rockets. But no coma was detected, no visible gas, no tail. Something was pushing it. One explanation proposed that radiation pressure, the tiny force exerted by sunlight, might have accelerated it. But for that to happen, the object would need to be extremely thin and lightweight, like a light sail. A light sail is not science fiction. It is real physics. In fact, humanity itself has explored the concept. The idea that an advanced civilization might deploy vast sails powered by starlight is entirely consistent with known physical laws. If such a civilization existed thousands of years ahead of ours, sending small probes across interstellar distances would not be impossible. After all, humanity launched Voyager 1 in 1977. Today it travels through interstellar space, carrying a golden record, a message in a bottle for the cosmos. If we can send one probe outward, why assume others cannot send probes inward? The famous Frank Drake formulated the Drake equation to estimate how many intelligent civilizations may exist in our galaxy. Even conservative assumptions suggest the Milky Way could host thousands. If even a small fraction developed advanced technology, interstellar exploration would eventually follow. And yet, skepticism remains the cornerstone of science. Extraordinary claims require extraordinary evidence. Perhaps ʻOumuamua was a fragment of a distant planet, torn apart by gravitational forces. Perhaps it was composed of exotic ices that evaporated invisibly. Perhaps nature simply surprised us once again. But what made this event historic was not proof of aliens. It was the shift in discussion. For the first time, serious physicists openly considered, even briefly, the possibility of artificial origin in peer-reviewed scientific discourse. Then in 2019, another interstellar visitor arrived. Borisov. This object behaved exactly like a comet should. It had a visible coma and tail. Its chemistry was familiar, which made ʻOumuamua even more mysterious. Soon, next-generation observatories like the Vera C. Rubin Observatory will scan the heavens with unprecedented sensitivity. Instead of discovering one such object every few years, dozens may be detected annually. When the sample size increases, the mystery will either dissolve or deepen. If ʻOumuamua was natural, then it was a rare cosmic artifact. If it was artificial, then humanity witnessed the first whisper of another civilization. Either way, the universe has spoken, and science must listen carefully. I am Michio Kaku, and whenever a mysterious object enters our solar system, it forces a deeper question, not just about the object itself, but about our cosmic solitude. If intelligent life is common in the universe, then where is everybody? This question is famously known as the Fermi Paradox, named after the brilliant physicist Enrico Fermi, who once asked during a casual lunch conversation, "Where is everyone?" The paradox is simple. The Milky Way galaxy is over 13 billion years old. There are more than 100 billion stars within it. Many of those stars are older than our sun. If even a tiny fraction developed intelligent life, and if even a smaller fraction developed advanced technology, then the galaxy should already be filled with evidence of their existence. And yet silence, no confirmed signals, no alien megastructures, no spacecraft hovering above our cities, just silence. But silence does not necessarily mean absence. It may simply mean distance, limitation, or misunderstanding. Let us consider a possibility grounded in physics rather than fantasy. Interstellar travel with massive ships carrying biological beings is extraordinarily difficult. The distances are vast, The energy requirements are enormous. Even traveling at a fraction of the speed of light, reaching nearby stars would take decades or centuries. But sending small robotic probes is another matter entirely. Probes require far less energy. They do not need food, oxygen, or biological life support systems. They can travel slowly for thousands of years without complaint. In fact, this may be the most logical method for any advanced civilization to explore the galaxy. Instead of colonizing physically, they may scatter intelligent machines across the stars. This idea leads to a fascinating concept known as self-replicating probes. Imagine a machine sent to a distant star system. Upon arrival, it mines local materials, asteroids, moons, comets, and builds copies of itself. Those copies then travel to new star systems, repeating the process. In theory, using exponential growth, such probes could explore the entire Milky Way in a few million years, a blink of an eye on cosmic timescales. The laws of physics do not forbid this. In fact, they permit it. And if that is true, then the question becomes even sharper. If intelligent civilizations exist, and if self-replicating probes are feasible, then why has none been clearly observed? Perhaps they are too small. Perhaps they are dormant. Perhaps they are designed to observe quietly. Or perhaps they are disguised as natural objects. When ʻOumuamua was discovered, some scientists proposed that its unusual acceleration could be explained if it were a thin light sail. A light sail is not magical. It obeys Maxwell's equations and the known principles of radiation pressure. Light carries momentum. When photons strike a reflective surface, they transfer momentum. If the surface is thin and lightweight enough, even sunlight can push it. This is not speculation. This is physics. Projects on Earth have already tested small-scale light sails in orbit. The concept is technologically plausible. Now imagine a civilization 1,000 or 1,000,000 years ahead. For them, sending countless thin probes across interstellar distances might be routine. Such probes could drift silently between stars, requiring no active propulsion once launched. They would simply ride the pressure of starlight. If ʻOumuamua were such an object, it would not necessarily be a spacecraft in the dramatic sense. It might not contain little green beings or flashing lights. It might simply be a silent artifact, a relic, a messenger. But skepticism must remain firm. Nature is extraordinarily creative. The cosmos is a laboratory operating for billions of years, producing phenomena beyond immediate intuition. Exotic ices, tidal disruptions of planets, collisions in distant star systems, all can produce fragments that defy expectations. Science progresses not by excitement, but by evidence. And so the mystery remains balanced between two powerful forces: curiosity and caution. There is also another possibility, one that is humbling. Advanced civilizations may choose not to interfere. They may observe quietly, following a cosmic version of what science fiction calls the Prime Directive, a non-interference policy toward developing civilizations. If that were the case, probes might exist not to announce themselves, but to watch, to collect data, to measure atmospheric chemistry, to listen for radio emissions. Human civilization has been broadcasting radio waves into space for just over a century. On a cosmic timescale, that is the faintest whisper. If a probe passed through our solar system thousands of years ago, it would have detected nothing unusual, just another planet with primitive life. But today, Earth glows with artificial radio noise. Our atmosphere contains industrial signatures. Our planet now carries the unmistakable fingerprints of technology. If probes exist, then Earth has only recently become interesting. This realization transforms the question. ʻOumuamua may not have been a probe, but it forced the scientific community to confront a profound truth. The search for extraterrestrial intelligence is no longer confined to radio telescopes. It may involve physical artifacts. The sky is no longer just a canvas of stars, it may be a highway. And the next object that enters our solar system may not merely pass through unnoticed. With upcoming observatories and improved detection systems, humanity is entering a new era, one in which anomalies can be studied in real time. If one day a truly artificial object is detected, the discovery would not merely be scientific. It would be philosophical. It would redefine religion, culture, politics, and identity. But until that day arrives, discipline must guide imagination. The universe does not yield its secrets easily, and every mystery must be tested against the unforgiving standards of physics. The question remains open: interstellar object or alien probe? If an advanced civilization were capable of sending probes across interstellar space, what would the physics actually require? The distances between stars are staggering. The nearest star system, Alpha Centauri, lies over 4 light-years away. That is nearly 25 trillion miles. With conventional chemical rockets, the journey would take tens of thousands of years. But physics offers alternatives. Nuclear fusion propulsion, antimatter engines, and light sails are all concepts grounded in established equations. Einstein's relativity sets the cosmic speed limit. Nothing can exceed the speed of light. Yet traveling at a significant fraction of light speed remains theoretically possible. A probe traveling at just 10% the speed of light could cross the galaxy in a few 100 million years. On a cosmic timescale, that is brief. Even more intriguing is the possibility of AI-driven probes. Biological organisms are fragile, machines are not. Radiation, vacuum, extreme temperatures, these are survivable conditions for advanced robotics. An alien civilization millions of years older than humanity would likely transition from biological intelligence to machine intelligence. Such a civilization might send autonomous explorers rather than living beings. These probes would not need to be large. In fact, smaller is better. The smaller the mass, the lower the energy required to accelerate it. Some theoretical designs suggest wafer, thin probes only millimeters thick but kilometers wide, light sails propelled by lasers or stellar radiation. Others imagine compact, dense objects built to survive micrometeor impacts and interstellar dust collisions. If ʻOumuamua exhibited unusual acceleration due to radiation pressure, then one must ask, was its surface unusually reflective? Was it thin? Was it engineered? Again, natural explanations exist, but the physics does not forbid artificiality. Another possibility is gravitational slingshot maneuvers. By passing near massive stars, neutron stars, or even black holes, a probe could gain tremendous velocity without expending fuel. The galaxy itself becomes a propulsion system. There is also the concept of dormant probes, sometimes called lurkers. These hypothetical devices would enter a star system and remain inactive for centuries or millennia, waiting. Waiting for what? For signs of intelligence. Earth has only recently begun emitting detectable technological signatures. If a probe were parked in the outer solar system, quietly observing, it might only now be activating. This idea sounds dramatic, but it is not inconsistent with known physics. The universe is vast. Monitoring from a distance is efficient. And yet, caution must prevail. Extraordinary interpretations must survive ruthless scrutiny. Spectroscopic analysis of ʻOumuamua suggested no clear industrial signatures. No obvious radio transmissions were detected. No course corrections were observed. But absence of evidence is not evidence of absence. Detection methods are limited. Instruments have thresholds. Observational windows are brief. ʻOumuamua was discovered only after it had already passed perihelion, the closest point to the Sun. By the time telescopes focused on it, it was already leaving, a fleeting visitor. Future detection systems will change this. The Vera C. Rubin Observatory will survey the sky with unprecedented precision. Artificial intelligence algorithms will analyze trajectories in real time. Anomalies will be flagged instantly. The next interstellar object may be studied in detail, perhaps even intercepted by spacecraft. Imagine launching a rapid response probe to Rendezvous with an incoming interstellar visitor, sampling its surface, measuring its isotopic ratios, searching for nanostructures or engineered materials. That would be a turning point in human history. If the object proves natural, science advances. If it proves artificial, civilization transforms. Until then, physics remains the ultimate judge. The equations of motion, radiation pressure, thermodynamics, and orbital mechanics do not bend to imagination. They either support a hypothesis, or they do not. ʻOumuamua sits at the boundary between anomaly and explanation. Interstellar object or alien probe. The universe has presented the question. Science must now gather the evidence. For if alien probes are possible, then the deeper question is not about engineering, it is about evolution. How long does it take for intelligence to emerge? On Earth, life began roughly 3.5 to 4 billion years ago. For most of that time, it remained microscopic. Multicellular organisms appeared only about 600 million years ago. Technological civilization, capable of radio transmission, has existed for barely a century, a blink. The Milky Way galaxy, however, is over 13 billion years old. Many stars formed billions of years before our Sun. That means alien civilizations, if they exist, could be millions or even billions of years ahead of humanity. Consider the implications. A civilization just 1,000 years ahead of ours would already possess technologies that seem miraculous. A million years ahead would be beyond imagination. A billion years ahead would appear godlike. In physics, there is a framework called the Kardashev scale, proposed by the astrophysicist Nikolai Kardashev. It measures a civilization's level of advancement based on energy consumption. A Type I civilization harnesses the energy of its planet. A Type II civilization harnesses the energy of its star. A Type III civilization controls energy on the scale of its galaxy. Humanity is not yet Type I. If a Type II or Type I civilization exists somewhere in the Milky Way, then interstellar probes would be trivial. A civilization that can manipulate stellar energy could launch millions of probes without effort. They could construct megastructures such as Dyson spheres, theoretical constructs first discussed by Freeman Dyson, to capture the full output of a star. Against that backdrop, sending a small probe to neighboring star systems would be insignificant. Now imagine such a civilization deciding to explore. Would it send crewed missions? Probably not. Biology is fragile, machines are resilient. Advanced civilizations may transition into post-biological forms, digital consciousness, artificial intelligence, machine-based life. In such a state, interstellar probes might not just carry sensors. They might carry minds. If ʻOumuamua were artificial, it might not be a ship in the science fiction sense. It could be an information packet, a data capsule crossing the galaxy, a silent archive, or perhaps something simpler, a reconnaissance device programmed to scan planetary atmospheres for oxygen, methane, and industrial pollutants, signatures of life and technology. Earth now broadcasts unmistakable markers of civilization. Our atmosphere has changed. Our planet emits artificial electromagnetic radiation. From a distance of dozens of light years, Earth would now stand out. If probes roam the galaxy, Earth has only recently entered their detection threshold. There is another sobering possibility. Advanced civilizations may not last long. Technological societies develop powerful tools, nuclear weapons, artificial intelligence, genetic engineering. These same tools carry existential risks. Self-destruction may be common. If most civilizations extinguish themselves shortly after achieving advanced technology, then the galaxy might contain relics rather than active empires, probes drifting endlessly, signals fading into silence, artifacts without creators. In that case, ʻOumuamua, if artificial, would not represent a thriving galactic federation. It would represent a fossil, a remnant of a civilization long gone. This perspective reframes the mystery. The question is no longer simply whether ʻOumuamua was a probe. The question becomes, what is the lifespan of intelligence in the universe? Physics allows interstellar exploration, but sociology and survival determine whether civilizations persist long enough to accomplish it. The universe may be filled not with empires, but with echoes. And each interstellar object that passes through our solar system may be either a natural fragment of cosmic chaos or a fragment of someone else's history. The silence of the stars remains profound, yet every anomaly invites deeper investigation. Interstellar object or alien probe. The answer lies not only in astronomy, but in understanding the destiny of intelligence itself. Jisr Hamzakan Nichi Par 5 Pesh Hai, Focus Engineering Detection Strategy, Our Future Missions Par Rahega. Part 5. If the universe is sending messengers through our solar system, then the real challenge is not philosophy, it is preparedness. ʻOumuamua was detected late. By the time telescopes focused on it, the object was already moving away from the sun at tremendous speed. Observational time was limited. Data was incomplete. That cannot happen again. The future of this mystery depends on early detection. Wide-field sky surveys are transforming astronomy. Advanced observatories now scan vast portions of the sky every night, comparing images with powerful algorithms to detect motion against the background of stars. Artificial intelligence systems flag anomalies within minutes. The next interstellar visitor will not slip by unnoticed. Once detected early, the next step becomes possible interception. Engineers have already proposed rapid response missions, spacecraft that remain on standby, ready to launch within weeks of detection. Using gravitational assists and advanced propulsion, such a probe could rendezvous with an incoming interstellar object. Imagine approaching such an object up close. High-resolution imaging, surface composition analysis, magnetic field measurements, thermal mapping, spectroscopy would reveal isotopic ratios. If those ratios differ significantly from solar system norms, the object's extrasolar origin would be confirmed beyond doubt. If microstructures were detected, repeating geometric patterns, alloys, nanotechnology, the implications would be historic. But even a completely natural object would be revolutionary. It would provide the first physical sample from another star system. There are already conceptual mission proposals designed specifically for this purpose. Some rely on chemical rockets with gravity assists. Others explore solar sails deployed near the sun to gain extreme velocity. A spacecraft diving close to the sun can use its immense gravity like a slingshot, achieving speeds otherwise impossible. Physics becomes an ally. The sun itself becomes a launch platform. Another idea involves placing telescopes at extreme distances from Earth, even using the sun as a gravitational lens. Einstein's theory of general relativity predicts that massive objects bend light. At approximately 550 astronomical units from the sun, the solar gravitational lens could magnify distant exoplanets dramatically. A civilization capable of such engineering would possess the tools not only to detect alien life, but to observe surface details on distant worlds. If humanity is contemplating these strategies today, then older civilizations may have implemented them long ago, and yet caution remains essential. Interstellar space is violent. Dust particles traveling at high velocity can erode surfaces over millions of years. Cosmic radiation degrades materials. Thermal cycling stresses structures. Any artificial probe traveling between stars would need extraordinary durability. ʻOumuamua showed no obvious signs of active propulsion. No radio signals were confirmed. No controlled maneuvers were observed. But detection methods have limits. Our radio telescopes scanned for narrow band transmissions, signals intentionally designed for communication. An advanced probe might use entirely different frequencies, encryption methods, or communication techniques beyond current assumptions. It might not transmit at all. Silence may be intentional. There is also the possibility that ʻOumuamua was not a probe, but debris. A fragment of a larger structure, a broken sail, a relic of some distant technological accident. Human civilization has already created space debris orbiting Earth. Scaled to galactic proportions, advanced civilizations might litter interstellar space with fragments of their own activity. Not every artifact must be purposeful. Some may simply be leftovers. The key moving forward is systematic observation. Catalog every interstellar object, measure their acceleration precisely, analyze their spectra thoroughly. Compare statistical distributions of shape and rotation. Patterns will emerge. If most interstellar objects resemble comets like 2I Borisov, then ʻOumuamua may simply represent a rare but natural anomaly. But if multiple objects display similar unusual properties, thin geometry, unexplained acceleration, extreme reflectivity, then the conversation changes. Science advances through repetition. One anomaly is curiosity, two anomalies are coincidence, three anomalies demand a new theory. The coming decades will provide that data. Humanity is transitioning from passive observer to active investigator of interstellar visitors. The next time an object enters our solar system from deep space, instruments will be ready. Missions may launch, samples may be collected, and the question, interstellar object or alien probe, may finally move from speculation to measurement. If an interstellar object were confirmed to be artificial, the consequences would extend far beyond astronomy. It would challenge humanity's understanding of itself and its place in the cosmos. For centuries, humans have considered themselves unique. Earth seemed the center of creation, and our technology was unparalleled. Yet, the discovery of a deliberate artifact from another star system would shatter that assumption. Philosophers, theologians, and scientists alike would be forced to confront a profound question: are we alone, or merely one of many intelligent civilizations scattered across the galaxy? The impact on culture would be profound. Imagine the headlines, "Alien artifact detected in the solar system." The public imagination would ignite. Governments, space agencies, and institutions worldwide would mobilize. Scientific priorities would shift overnight. Funding for space exploration would surge. Humanity would suddenly understand that the cosmos is no longer a distant backdrop, but an active environment teeming with possibility. The psychological implications would also be complex. Some would feel fear, the existential fear that we are being observed by civilizations far older and more advanced. Others would feel awe and inspiration, the realization that intelligence can survive across the vastness of space and time. Educational systems would adapt. Children would learn not only about the solar system, but about interstellar objects, alien technology, and the physics of long-distance travel. Science fiction would be transformed into science fact. The line between imagination and reality would blur. Economics and politics would shift as well. Resources might be allocated toward rapid response missions, new telescopes, and interstellar propulsion research. Nations could cooperate on an unprecedented scale, driven by the common objective of understanding the cosmos and our place within it. Yet, caution would remain essential. An artifact could be inert, harmless, and passive, a message in a bottle drifting silently through space. But it could also carry unknown hazards. Radiation nanostructures or automated mechanisms could exist beyond human comprehension. Ethics and protocols for engagement would need to be established carefully. From a scientific perspective, the confirmation of artificial origin would revolutionize multiple disciplines. Astronomy, astrophysics, and planetary science would gain direct insight into the technology and engineering practices of a civilization far older than our own. Material science could be transformed by the discovery of previously unknown alloys or composites designed to survive interstellar space for millennia. Astrobiology would finally move from hypothesis to tangible evidence. Chemistry, biology, and physics would converge in the study of interstellar technology. Researchers would examine isotopic ratios, surface textures, and structural geometry for patterns indicative of intelligent design. The very concept of the Fermi Paradox would shift. Silence would no longer imply absence. Instead, we would recognize subtle evidence in physical objects, demonstrating that advanced civilizations have mastered stealth, patience, and long-duration observation. Ultimately, the philosophical lesson is humility. Humanity, still young in cosmic terms, would recognize that intelligence is rare, precious, and capable of surviving across unimaginable distances and timescales. We would glimpse the continuity of life and technology in a universe that spans billions of years. ʻOumuamua, whether natural or artificial, has already served as a catalyst. It has expanded our perspective, challenged our assumptions, and prepared us for the possibility that intelligence is not confined to Earth. The universe is vast, its secrets are patient, and one day, through observation, measurement, and courage, humanity may finally understand whether we are alone or being silently watched by the first visitors from another star system. Looking forward, the study of interstellar objects represents a turning point in human history. ʻOumuamua was not merely a curiosity, it was a harbinger of a new era in which humanity becomes an active participant in the exploration of the galaxy. The tools at our disposal are evolving rapidly. Next, generation observatories, powerful telescopes, and AI-driven data analysis will allow detection of anomalies long before they pass the solar system. Missions may be deployed in weeks, not decades, to intercept interstellar visitors. Instruments will measure composition, geometry, and radiation in real time. If even one of these objects proves artificial, the implications are staggering. We would finally have confirmation that intelligence is not unique to Earth, that life capable of technological mastery can emerge, survive, and explore across the vast distances of space. Physics provides the framework, but imagination gives us direction. Radiation pressure, hyperbolic trajectories, light sails, and gravitational slingshots are not science fiction. They are real phenomena governed by the laws of nature. They are the tools any advanced civilization could use to send messengers across the stars. At the same time, caution and skepticism remain our guides. Extraordinary claims demand extraordinary evidence. Each interstellar object must be analyzed carefully, measured precisely, and interpreted scientifically. Natural explanations must be exhausted before artificiality is seriously considered. Yet, even in the absence of definitive proof, ʻOumuamua has expanded humanity's horizon. It has forced us to reconsider the nature of intelligence, the longevity of civilizations, and the possibilities inherent in cosmic engineering. Perhaps the galaxy is filled with artifacts, silent witnesses to civilizations long gone. Perhaps they are scanning us now, observing quietly as we awaken to our own technological potential. Perhaps ʻOumuamua is only the first of many objects that will challenge our assumptions and broaden our understanding. The universe is patient, vast, and indifferent, yet it offers clues to those who look carefully. Each anomaly is a message, whether natural or artificial, urging humanity to explore, question, and dream. Interstellar object or alien probe, the question remains open, but the pursuit of the answer is transformative. It compels science, philosophy, and society to evolve together. It reminds us that humanity is not merely a passive observer of the cosmos, but an active participant in its unfolding story. The coming decades will test our ingenuity, our curiosity, and our courage. We will map the trajectories of interstellar travelers, intercept them if possible, and perhaps uncover the fingerprints of intelligence beyond our own. And when that day arrives, humanity will have stepped fully into the cosmic arena. No longer confined to Earth, no longer bound by our solar system, we will finally engage with the vast, mysterious, and potentially inhabited universe. The message is clear: the cosmos is not empty. It contains secrets, travelers, and perhaps intelligence that has already traversed the stars. The pursuit of understanding those mysteries will define the future of science and the destiny of civilization itself. Interstellar object or alien probe, the search continues.